From biomedical imaging to number representations and general-purpose vision, today's papers reveal a common theme. Strong models often learn more than they seem. We'll explore how negative controls can stabilize domain adaptation in microscopy, why language models converge on surprising number patterns, and how image generators can double as powerful vision learners. Together, these studies show AI systems discovering hidden structure, adapting across domains, and blurring the line between generation and understanding. Let's explore the first paper, Closing the Domain Gap in Biomedical Imaging by In-Context Control Samples. The paper identifies batch effects in biomedical microscopy as a domain adaptation problem where standard deep classifiers fail on new experimental batches because batch norm statistics become biased by class mixture changes. On JumpCP, a ResNet 5.0 reaches 0.939 plus or minus 0.005 inches domain accuracy, but drops to 0.862 plus or minus 0.06 on unseen batches. A frozen CAMAE linear probe is worse at 0.747 plus or minus 0.006. The core contribution is control-stabilized adaptive risk minimization with batch normalization, CSRM-BN, a meta-learned, unlabeled test time adaptation method that conditions BN statistics on both perturbed samples and always available negative controls from the same batch. Technically, it extends RMBN by computing per layer mean variance over the union of controls and query images, turning control samples into in-context calibration data rather than post-hoc correction. The key novelty is the bias variance argument. Using only perturbed samples gives an estimator biased by mean class effect, while controls-only estimation is unbiased but high variance when control counts are small. CSRMBN shrinks bias by a factor L divided by M and variance by 1 divided by M, where M equals C plus L. Empirically, this stabilizes adaptation under small context sizes and label shift. Under mild within source batch shift, RMBN and CSRMBN nearly close the domain gap, with RMBN at 0.935 plus or minus 0.018 and CSRMBN at 0.93 plus or minus 0.019, essentially matching in-domain performance. Under severe label shift, CSRMBN is markedly more robust. At alpha equals 0.01, it attains 0.894 plus or minus 0.022 versus 0.228 plus or minus 0.009 for RMBN and 0.156 plus or minus 0.01 for TENT. Across cross-source transfer, label-shifted target batches, and a Levite backbone, CSRM-BN remains the most stable BN-based method, showing that negative controls can function as a reliable in-context anchor for domain-neutralized biomedical imaging. Let's explore the second paper, Convergent Evolution: How Different Language Models Learn Similar Number Representations. Wu, Zhou, Belkin, Shaoran, and Jia show that number embeddings in language models exhibit two distinct levels of convergence. At the spectral level, discrete Fourier analysis of embeddings for integers 0, 999 reveals robust spikes at periods t equals 2, 5, and 10 across heterogeneous systems. GPT-2, GPT-OSS, Llama 3.4, DeepSeek v3, Mamba 2, Falcon Mamba, XLSTM, Kimilinear, and even static word embeddings such as Glove, FastText, Word2Vec, and PPMI. Strikingly, the raw corpus frequency distribution of number tokens already contains the same periodic spectrum, so Fourier spikes reflect training data, tokenization statistics rather than necessarily learned numerical structure. The authors prove a sharp separation theorem. Non-zero Fourier power at period t is necessary for mod t structure, but not sufficient for linear decodability. They define geometric convergence as linear probe separability of n mod t from the embedding En. On 300M, parameter models trained on 10 B-FineWeb edu tokens with the Llama, 3 tokenizer, transformers, and linear state models such as Gated, DeltaNet, and Mamba to reach strong mod t decoding, while LSTMs can show even larger Fourier spikes yet remain at chance. For example, under the original setup, a transformer attains Cohen's kappa equals 96 for mod 2 and 85 for mod 10, whereas the LSTM is near 0 despite stronger t equals 10 power. Controlled data ablations show geometric convergence depends on text number co-occurrence, cross-number interaction, and context length. Spectral convergence survives even when all number co-occurrence is destroyed by unigram replacement. Architecture and optimizer matter too. Muon generally helps transformers and gated deltanet, but not uniformly Mamba too. In addition, 9-digit addition forces both spectral and geometric convergence across optimizers, while 3-digit single token addition does not, indicating tokenization can create or eliminate modular learning pressure. Let's explore the third paper. Image generators are generalist vision learners. Image generators are generalist vision learners argues that large-scale image generation pre-training already learns transferable visual representations and demonstrates it by instruction tuning Nano Banana Pro into Vision Banana with a small amount of vision task data while keeping the original generative mixture. The key technique is to recast perception as image generation. Segmentation, masks, depth maps, and surface normals are emitted as decodable RGB visualizations, with prompts specifying color maps or invertible encodings. For metric depth, the paper uses a bijection from depth in 0-infinity to RGB via a Baron-style power transform. Lambda equals -3, C equals 10 divided by 3, plus edge of cube interpolation, enabling exact decoding back to metric values. Without task-specific architectures or bespoke losses, Vision Banana reaches or exceeds specialist models on multiple zero-shot benchmarks. Cityscape semantic segmentation, MIOU 0.699 versus 0.652 for SAM3, RefcoCog UMD referring segmentation, CIOU 0.738 versus 0.734 for SAM3 agent. ReasonSeg GIOU 0.793 versus 0.77. Metric depth average, delta 1 equals 0.929 versus 0.918 for depth anything 3, and surface normal estimation mean angular error, 18.928 degrees versus 19.642 degrees for Lotus 2. Instance segmentation on SACO. Gold is competitive at PMF1 0.54 on a 500, query subset versus 0.552 for Dino X. Crucially, the model retains generation quality. It scores 53.5% win rate on GenAI Bench and 47.8% on ImGetIt against the base model. The paper's central novelty is that a lightweight instruction tuning layer can unlock hidden visual understanding in a pure image generator, suggesting generative vision pre-training can function as a unified foundation for both vision understanding and image synthesis. That's a wrap on today's AI paper highlights. Thanks for watching.